Should we watch all 7 hours? This is the, well, actually for a long time this was the short version of the game. Okay, so, all right, let's start. So, so cricket. Let's talk about cricket. So the traditional version of the game is 5 days long. It's a test. They're called test matches. And they're about 6 hours a day, 3 2-hour sessions. This is hard. This is physically, absolutely, it's quite hard. So, 30-hour match, which can end in a draw. And that's it. Which is much more like war. So that's kind of not unreasonable. Anyway, the one-day matches are fast. They're only 7 hours long. And this was the semi-final at the SCG. Australia beat India last night. I don't know, not anywhere near as spectacular as the New Zealand-South Africa game. Anyway, so Australia, you want to know this. Australia's playing New Zealand at the Melbourne Cricket Ground. That's about 100,000 people on Sunday. So Saturday night, about 11:30, you should, get some dubious feed from Belgium, and you can watch the cricket. All right. I'll tweet the highlights. All righty. So today. All right. I don't think there's anything else to show you. Let's go. So today we're going to talk about. This is ridiculous. So on the board behind me is this picture, which I just tweeted. So, okay. All right. Strange. Let's see, so we're going to solve this eigenvalue problem, right? This is a classic, famous problem in science, actually, and linear algebra has its own version. You'll find it everywhere. Quantum mechanics has it. Fluid dynamics, you'll find these kinds of things, all sorts of places. Economics, wherever you want to go. You'll find people running around with these equations, sometimes crazily. And it is this business, AV equals lambda V. It's easier to point here. So again, square matrices. This is a vector V. This is the same vector V. That is my V. That is a V. It's not a U. It's a V. U's look like this. That will be a U. There will be U's later on. X and Y, U and V. Right. I really wanted to get into Greek letters, but we're not going to do it. Okay. Okay, and that lambda, that's a number. So we're going to find the vectors V, and this is what we talked about on Tuesday, that A really likes. It preserves those directions. A times V equals some number times V. And they're very special. The numbers, the lambdas are very special. These are called eigenvalues, and these are eigenvectors. And we will get into this now, and then we have to take a detour. It's kind of like in the movie where the person starts driving and kind of goes off into some tangent. That's where we'll be. It's going to be in a determinant world. Determinants are these strange numbers. Every square matrix has a determinant, which is one number. And there are lots of ways to get at what that is, but I'll give you a very geometric, fundamental way. Why they matter for this equation, and we'll take a couple of lectures to do this, but how to compute them from the ground up. All right. Okay, that's today. Let's see. I'll get rid of that thing for you. Click mute. And what am I doing? Pushing the button. Which button? Oh, this one. Okay. All right. Exciting. Okay. Things. So we played around with this matrix the other day. 1, a half, 1. We okay? So, it's exciting. I know it's exciting. All right. Above all, linear algebra is emotional. Okay, let's see. So, eigenvectors and eigenvalues, eigenthings. And these things, there are 3 of these. values, vectors, and much more spaces. These guys live in here. There's a bit of a funny way people present this. They'll say there is an eigenvector for, right? There's sort of a sense that there's just this one eigenvector, but it's actually a basis vector. So we will get all that because we know all about null spaces. Right. Okay. So let's just refresh our brains here a little bit. Huh. Oh, look. I can point to the ghost version here, right? So this character, A equals 1, a half, 1. So previously on Buffy the Vampire Slayer, we found that if we multiply A times, and we were just messing around, Monks told us to do this, A times 1, 1, and let's make it equals 3 halves times 1, 1. And more generally, this is A times minus 3. It gives us the same vector back with the 3 halves, minus 3, etc. Right, this kind of thing. We also found there was one other vector, and we're not sure about this yet. We haven't proved this, but we noticed there was one other, and it was a half. Right, so this is going to be our eigenvalue lambda. This is going to be an eigenvector v. This is very special. E value. Some people they'll just say E. Eigenvalue, right? This is the matrix selfie. And V, this is an eigenvector. So before we go on, what would be a really good eigenvector to choose? Right? We can have minus 3, we can have 17 and 17, we can have anything as long as these two numbers are the same. A will give you that vector back. A times that vector will come back, and it'll multiply by 3 halves. So A just looks like 3 halves. Here, A just looks like a half as it acts on that vector. So what would be a kind of a really nice choice for, right? We could have 7, 7, 30, 30. Yeah, great. All right, so a really a nice choice would be, and we'll see these things will pop out, would be to say this, lambda 1 equals 3 halves, and V equals 1 over root 2. You'll see that people don't always worry about this, but it's a unit vector. Now there is one degree of freedom left though, right? Which is, we made it length 1, so there's no information. It's all just about the direction. There's one other thing we could flip here. We could have a sign, right? We could change the sign. So that's true. So I'll just put that in there. We'll just use the nice one, okay, in general, the one that we like. We have something against negatives. Lambda 2 is a half, and V2 in that case would be in the same kind of thing, 1 minus 1, or 1 over root 2 minus 1, 1. Okay, right, so the game is, this is due to Monks. So how do we get around having some, wizened character whisper the truth to you? So the game is how to find these vectors and values, right? Algorithmically, right, with a process. I'll say algorithmically. What's the way to do it? Okay, so, all right. So fair enough, this is where we were. And we're not sure that there are no more. We kind of had this picture up here. It looked like it from the flow that I told you. It didn't look like there were any other directions. And so that's a general thing we'll see in a second, that the largest number of eigenvalues you can have, so every square matrix has n eigenvalues, right? There's a very sad aspect that not all of them have n eigenvectors, so we'll have to cope with that. Right. Some matrices are bad. Okay. Okay, all right, so maybe I'll put that one down. So how do we find these things? Okay. Let's solve, we know it's something like this. Let's solve AV equals lambda V. So we know this. This is the only thing we know. A, it's an n by n. We do not know this. We do not know this. It's a v. I'll write v. And this is a scalar. We do not know this. So there's a lot in that equation. That's a bit funny, right? Before we had a different kind of problem. So before we've struggled with this, ax equals b, different thing. We're trying to figure out how to combine columns of A to make B. So here we knew this one, we knew A, and we didn't know X. So it felt like we had a little more. All right, different game though, different game. And this, of course, is a square matrix. This could be rectangular. This is a square. All right. So always with the monks. So first thing we can do, there is one small step that opens the game up with this equation, right? So we want to find the v's for which A times V is just some multiple of V. All right, so, all right, well, maybe it's a monk thing, but we could play around with this in different ways. I don't know. See, I'm going to tell you the way to do it, but I'm trying to think of other ways to drive the bus off the, like there are lots of, you could sit here and stare at this for a long time. Many monks just died, just looking at this. Okay. And then one of them said, what if we put them on the same side? He was burned at the stake, and then about 100 years later, someone said the same thing. And they're like, okay. It's a harsh world, monk mathematics. Okay. All right. Also, okay, we've got this. Okay, all right. So we kind of got them on one side. We've got something equals 0. That's not bad. We like 0. This could be a null space type problem. So can we do this? Could we like to factor things? I'm waiting for lightning bolts to hit me, but apparently they don't reach through this building. Anyway. I did something really bad. What did I do? I mean, not the other things. This thing, just on the board right now. Okay. What's it going to be? So this is, oh, I see, right, yeah. That's it. We've got the order right. The order's okay, because it's going to be A times V. Anything wrong with this? Yes? Right, so very good. So this is, if you like, a 1 by 1, and this is an n by n. Right, so we're adding a giraffe to a hippopotamus. That's bad. Okay, so, no. So that monk was burned at the stake. All right, and then 100 years later, someone said, let's do it, but not what that other person did. Let's, pretty cruel world. Okay, so so we could do this, but let's do something sneaky first. The sneaky things, always with the sneaky thing. We're going to say, well, let's put an identity matrix in there. Classic math stuff, don't touch that bit, and you're like, what? Okay, no. So V is the identity times V. Fine, we can just do that, right? This is going to work out, it just gives you V back. So that was okay. So now we have it. Now we're on board. We can combine these two things, right? Now we can combine them. This thing, that's a matrix. It's n by n, multiplied with a lambda, and we can combine those. So now we can do the factoring. Aha. So monks. Now everything works. N by n. This is an n by n, and this is an n by 1. So if you think about what we're doing here, we're subtracting lambda from the diagonal of A, the main diagonal. So our example, our little friend here, 1, 1, a half, half, So that equation is going to behave as 1, a half, 1. That's A there. And then we'll have minus lambda times the identity. Oops. This is really just fantastic. OK, and then with V1, we'll call it V1 here and V2, which is a little awful, but we'll do it. And then these are 2 zeros. Let's write the whole thing out. So this is something we can handle, actually. This is all good. So now we are at the stage of, let's combine it. We have 1 minus lambda. That's this part. Zeros on the off diagonal. So put a half here, and then there's a 1 minus lambda here. So all of this times V1, V2 equals 0, 0. So we refuse to learn anything new, and we get it back into an AX equals B problem, which we can solve. Null space problem. I know, I said that funny, but we don't have to. Null space problem, yes. You put smiley faces next to it, frowny faces, whatever. Okay, this is good. So you can see how this will generalize. We have 100 by 100. We take that matrix, 100 by 100 matrix, subtract lambda off the diagonals, multiply it by V1 down to V100, and then you have zeros over here. Null space problem. Now, of course, we have lambdas in here. So what's the... There's still something we need to unlock. There's still a sneakiness to this. So what if this was invertible? What if we choose lambda such that this is invertible? Imagine lambda is a dial now. We can dial lambda from minus infinity to infinity. Just dial it around. So we just choose lambda. We say 7. We don't choose one of these special ones, a half or 3 halves. What? Okay, we'll get to it, I suppose. But you can choose, there are many lambdas you can choose for which there's an inverse of this matrix. It exists. And if an inverse exists, you can multiply both sides by the inverse, and therefore, what will happen? If I have an inverse for this matrix, and I multiply it here, it turns this whole thing into the identity. So V equals 0. So there are all these lambdas for which there'll be an inverse for this equation, or this matrix, this blob we're making. Then you can use it to show that V equals 0. There's no null space for that lambda. I have to say this a few times. There's no null space. So that means there's no vector V that works for that lambda. Right? So if we said, okay, we want 7 here, and we have our matrix, this one, there's no solution. The only solution is V equals 0. Right? Because V equals 0 works. V equals 0 always works. 0 and 0. All right, so a big deal is we want to find values of lambda for which V not equal to 0 is a solution. Right? There are some V's there, which is equivalent to saying the null space of A minus lambda I is not equal to just 0, or the dimension of the null space of A minus lambda I is greater than or equal to 1. Connecting it back to the AX equals B problems. I'm going to say all these things. That's my next bit. Another word we have is this. We would say that the A minus lambda I is singular. That's a word that we had for a long time ago, which is to say that the inverse minus 1 does not exist. Same things. These are square matrices, so we can talk about inverses. And then the last thing is that the determinant and this is this precursor thing, determinant of a minus lambda I equals 0. So this is more soon, right? Whatever this thing is. If you haven't heard of it, doesn't matter. It's a new thing. It's a number associated with every square matrix. So all of these things are equivalent. So let's solve this one. And then we'll see why it's a little bit of a hard business. Okay, so, all right. Okay, let's find the E things, eigen things for, okay. So, okay, let's find the eigen things, very fine, very enjoyable, for A equals 1, a half 1. So as soon as you've got your square matrix, someone says find the eigenvalues, then you're off, right? So you set it up like this every time. It's going to be 1 minus lambda, a half, 1 minus lambda, 0, 0. This is our first way to do it because we know about null spaces, right? This is not the way we're going to do it eventually, but this is going to be the first way to do it. Right. So we use our old approach. And there'll be something, we've done these row operations a lot, there'll be another benefit for the way we do row operations. We have a very principled way of doing row operations, right? So this next step, it's row 2 prime. Let me write that in the same, row 2 prime equals row 2 minus something times row 1. So I'm going to put a note here that this form remains important and will help us when we get to these determinant things, which are very, very strange. Okay. But I'll give you a nice way to think about them. So what is this? So it's a half divided by 1 minus lambda. And part of what this example will figure it out, but part of what this example will somewhat show is that this is nasty. This is we're already into a bit of a mess because now we've got a lambda on the bottom. And that's just going to get worse and worse. We have a 100 by 100 matrix, we're going to have lambdas all over the place underneath. We have to have them, but would be nice if they were multiplying each other on top, perhaps. Let's say that. So, I've got this right, I think. Okay, yes? Tell me if it's wrong. So, the first row stays the same. Half, 0. It's a half minus a half times 1 minus lambda, right? So that we've guaranteed that this equals 0. And let me write it here. It's a half minus 1/2 divided by 1 minus lambda times 1 minus lambda. We guaranteed that's the setup. Trying to create a 0 there. Let me try and get this story about why we have to have a null space that's not 0. That's going to come out, hopefully. Okay, so what's this one here? So it is 1 minus lambda minus this bit here. So, all right, it's 1 minus lambda. I'll just write it out as the whole thing. 1 minus lambda, and then there's a half times a half divided by a half squared divided by 1 minus lambda. I won't do that. So you see that? That's one thing in a box here. Put it in a box. And we have 0 over here, null space problem. So this is just a 2 by 2. Already we've got a bit of a mess. So this is messy. But we press on because we're using the tools in our bag to start with. Okay, all right. Any questions about this? Trying to connect it to all the things you've done already, which I'm trying to remember when I learned linear algebra. I don't think it just seemed like a big mess. Which okay, all right. No, it's true, but it wasn't connected like this. Okay. Yes. Okay, so so this is not, it's not looking like fun. We want to have fun. So we're interested in when this is 0, this blob. When this is 0, we've got zeros across here. The rank of this matrix is 1. We have a null space that's non-trivial. Okay, so. Right, we want a nice null space. So not just this little sad thing here, not 0. So what have we got over there? 1 minus lambda minus a quarter on top, 1 minus lambda on the bottom. Let's find the lambdas for which this is true. Okay? So a little bit of messing around. We can put, so 1 minus lambda equals a quarter. 1 minus lambda on the bottom, put this on the other side. Bring this over here, 1 minus lambda squared equals a quarter. Square root of it. More lightning bolts, why? What should I have? Plus or minus? And it's the ghost of the monks. Okay, and then we have this business. And so we then have lambda, and I can put this 1 on the other side. I can flip the signs. Fine. 1 plus or minus a half. 1 plus or minus a half. Half or 3 halves? Yes. The sound from the heavens, right? Okay. Lambda 1 equals 3 halves. I'm just going to pretend that happened. Okay, lambda 2 equals a half. It's a funding problem, you know? Okay. It's true, they used to have choirs, all sorts of things in lectures. Okay, all right. That's the pure mathematicians. They get a little too carried away. Okay, let's see. So lambda 1 equals 3 halves. Smoke machines. That's 70s? Totally, smoke machines. Lambda 1 equals 3 halves. Lambda 2 equals a half. So we'll give them numbers now. We'll say there's lambda 1 and lambda 2. I did once have a student who's 6'10", who gave a talk once at another college and managed to have a smoke machine brought into company's talk. Wow, just amazing, great guy. Okay, lambda 1 equals 3 halves, lambda 2 equals a half. So they popped out. So these are special. These are special. And now we've got a little machinery going. We didn't have to use the monks. Well, I mean, they helped us. But now we have a system, right? This we're going to avoid because that's going to hurt too much. All right, but let's carry on. This is exactly how you do it, except for, right, once you get to here, this next part is going to be the way you'll do it all the time. Let's find the vectors associated with these. So the next step, so these are the eigenvectors, eigenvalues. Right, so the next step, we do one at a time, and we take lambda 1 equals 3 halves, is to find the, actually it's really this, the eigenspaces. People always say find the eigenvectors, but you're really finding the eigenspaces. So lambda 1 equals a half. We said we wanted a null space, right? We said we wanted a null space that was not boring. So we're going to go back to our equation. Right, so we substitute lambda 1 equals a half into, and I'll write it out, 1 minus lambda, a half, 1 minus lambda, this equation. And then lambda 2, we'll do the same thing. So let's do that. So 3 halves. So we're putting 3 halves in here. There's a minus a half, and a minus a half. What do you notice about these two rows? Row 1 and row 2 now. They are, right, they're just a sign change. They're just a multiple of each other. That's always going to happen for 2 by 2s because once you've found a lambda 1, once you've found lambdas that give you a 0 row, then that means you had to have had these 2 rows be multiples of each other. right? For this row to just completely wipe out this row, it had to be just a simple multiple of it. All right, so this is a little note. It's not true for 2 by 2s. Rows will always be multiples of each other in this part of the calculation. And so you don't have to actually even worry about, right? This row doesn't matter. It doesn't tell you anything new. Nothing new. Nothing extra here. But this is only for 2 by 2s, right? Not n by n's, n greater than or equal to 3. So don't get carried away. Okay, so we've got minus a half v1 plus a half v2 equals 0. That's what this equation says, right? We have a pivot free. We've got all that good business. You could do everything like that again. This is the pivot variable. I'm going to say it because everything's the same. So we express the pivot in terms of the free, and we could get rid of the halves and all those sorts of things. We have v1 equals v2. So we've got out our business, right? So the thing that we wanted. So it's v1, v2, replace the, you don't have to do all this, but replace the pivot variable in terms of the free one, v2, v2, equals v2, 1, 1, which is what we had per monks. Okay. So we say, so an eigenspace, and you'll see people will be just lazy in the way they do this. It's fine, it's okay. For lambda 1 equals 3 halves is all v in R2 such that v equals, different ways to write this, some multiple of 1, 1. And we say an eigenvector. People will sometimes say the, which is just kind of wrong. An eigenvector for lambda 1 equals 3 halves is a basis vector. And that will be, we can say v, we can normalize it. Normalization is good, but we'll just put this, right? Or with a little hat, we'll do the normalization. If we want normalization, we'll do it. But this, we're fine with this as well. Okay, good. So the other one. So let's do the other one. Lambda 1 equals a half. That's a good calculation to work on yourself. You see what happens here? Lambda equals a half. It's going to be a half, half, a half, half. So once again, the lines are the same as each other. So we get a half, a half, a half, right? And, right, calculate, insert calculations. Well, all right, I'll do it, sorry. Yeah. So we have a half v1 plus a half v2 equals 0. This is our pivot, this is our free. This one doesn't matter because it's just a copy. And so we'll end up with v, and in this case it's v, we're going to call it v2, but let's do it like this. V is an element of R2, and this is the eigenspace. You can see what it has to be. V equals some multiple of 1 minus 1. C is an element of the real numbers. And then we could choose, so this is an eigenspace. So let me write it properly. This is an eigenspace. This is an eigenspace. It's great, awesome, for L2 equals a half. So any vector in this space it likes, and then we'll write V2 equals 1 minus 1 is good, or we might get carried away and say let's normalize it, and we'll have this one. All right, so this is now sort of proof for this particular example that there are only these two eigen directions, which are represented as eigen subspaces, eigenspaces. There are only two eigenvalues. And let's see. So in fact, kind of what's happening here is this picture. Okay, let me draw this. So if we have lambda here, and then we have the dimension of the null space of A minus lambda I. Okay, so we're going to tune lambda across here. So we could do that, right? We just go back and we could tune lambda. Make any lambda we want. Fine. And what you see is the dimension of null space is 0. This is 0. Until we get to a half and 3 halves. And we'll do this thing, so I'll put a little circle there and a little circle there. And here the dimension is 1. So it's a funny, this is a discontinuity. Discontinuity. Okay, like my brain. Okay, so see what's happening? We're dialing lambda across, and we're trying to see if there's a null space. No null space. So all along here, an inverse, A minus lambda I minus 1 exists in these spaces. And if it exists, so if true, then we can always do this, right? So we have this equation, A minus lambda I times V equals 0. I said it in words before, but we'll say it. So now we're going to pre-multiply both sides by the inverse, right? If true, then we can do this, pre-multiplying by the inverse. And that's a V here. And then on the right-hand side, we've got A minus lambda I minus 1. Again, we're proving this for things that are billions of, doesn't matter how big they are. A matrix times its inverse. It's the identity. So the identity times V equals this blob, which is a matrix times 0. It's 0. So there's a hat on that one. So V equals 0. That's the only solution to that equation. V equals 0 always works. It always works. But we want something that has some substance, right? We want a vector that really does what this original problem is saying. A times that vector is lambda times that vector. And A times 0 equals lambda times 0. That's not very exciting. All right. Does this sort of make sense? It's connecting it back to all the goodness you've done before. Computing eigenvalues can become very mechanical, right? You can just do it. But you need to understand the whole picture here. And if you like, let's add some big picture goodness. So at these points, it looks like this. Null spaces exist, right? And out here, it's like this. No null spaces. If you're fans of the big picture. Okay, A times X goes that way. A is an n by n, so it's mapped. You can think of it sending a vector x to some other vector x prime within Rn. Right, so these are all the same sizes. Okay. So, in principle, this is all fantastic. I know that's what you're thinking. And, but you're saying that looks kind of messy. Yes. Okay. So here's another, I'll add a couple more comments. I'll just mention a couple of matrices, and then we'll start talking about determinants. So these vectors, 1, 1, and 1 minus 1, or the normalized ones, or they are a natural basis. This is a basis for a particular action of A. Right, so we'll come back to this later. So this is kind of an observation. This is, that 1, 1, let's say that, and 1 minus 1 are a natural basis for A when we think about A times X, what A does to a vector. This is really the right way to express it. So we'd like to express, it's best to express in terms of eigenvectors. And we saw that in the last lecture. Right, because then A times an eigenvector is simple. It's just some number times that eigenvector. Right. So we're going to come back to this. It's a better natural, it's the right basis, right? We have our 1, 0, 0, 1 basis, that's underlying everything. We need some structure. But any given A will have its own preferred basis. All right. So a couple of example, so just a few example, a few example matrices. Some special ones. I'll just sort of rattle these off. You can think about these. So let's say A equals the identity. And let's take just 2 by 2. Lambda 1 equals lambda 2 equals. So this matrix multiplying any vector just gives you the vector back. Right? So we can think, if you go through, you'll find out that it loves this. It has eigenvalues 1. Gives you the vector back, right? A times x equals 1 times x. And it has no preferred direction. It likes all directions. So you can, depending on how you compute it, you can say v1 equals 1, 0, and v2 equals 0, 1. So it's always worthwhile to think about the sort of trivial or the simple examples. The end examples, okay. And you can go through and compute it. This is a, okay, projection matrix onto 1, 0. 1, 0, 0, this thing. Right, so this takes vectors. Here's an example. Here's x. And this matrix times some vector x will just return the first number, right? So p 1, 0 times x1, x2 just equals x1. It's a projection matrix. Onto the x-axis. Projection onto the x-axis. We've thought about all sorts of other projection matrices. This is a very simple one. So it's going to send it to here. Right? This is A, this is P. I'll just write as P times X. So that one has, you can compute this. This one has lambda 1 equals 1. And we could say V1 equals 1, 0. So it likes that direction. It keeps that direction. Lambda 2 equals 0. And V2 equals 0, 1. So encoded in this lambda 1 equals 1 is it just preserves that direction. Whatever vector is attached to it, it likes that direction. It doesn't change it. It crushes this direction. It's got a 0. It goes, squishes it. So the projection, the idea of projection, which we've thought about so far, there's a view of it in terms of eigenvalues and eigenvectors. And the eigenvalues will all be 0s and 1s. 0s are for the directions that it squishes, 1s for the ones that it preserves. What else? This is a weird one. Rotation matrix by 90, let's say by pi over 2. 0, 1, minus 1, 0. Did I get that right? Is that right, people? So we've got a vector. Let's draw a picture. So we start here. We've got this one. It's 1, 0. I think I want well, let's make it minus pi of 2. So this thing multiplying this guy gives us 0. And then a minus 1, so down here. Yeah, that's what I've done. So this is a rotation by minus pi over 2 times 1, 0. Be minus 1 and 0 the other way. All right, fine. okay? So it likes to do this to vectors. So it's going to turn this one right angles, would go boop, this way. So it doesn't have direct, it changes every vector, right? There are no, it doesn't have preserved, so rotation can't preserve, this, you can think of it like this, can't preserve any direction. But mathematics, you know, we're not going to, you can figure out how to compute this after I show you determinants, but because math, we end up with lambda 1 equals lambda 1 and lambda 2 equal plus or minus I, square root of minus 1. So that should make you a little sick. But it's true that, in general, rotations are connected to the imaginary numbers. Electrical currents, all sorts of things are encoded with these things, right? Yep. A little bit bananas, but this is there's all this sort of business, right? E to the I theta equals cos theta plus I sine theta. All of that sort of stuff. Rotation, madness. Okay, so that's an odd one, but if you start getting out imaginary numbers, there's an aspect of rotation in what that matrix does, right? And that's a very fundamental kind of matrix operation. Literally in the Matrix, the movie, right? Okay, yeah. Okay. Wow, that's pretty bad, isn't it? Okay, so let's see. We are on to. Let me just summarize. I have a few things here. Right. So a little summary. So types of lambda, types of e-values, eigenvalues. Just kind of classes of them. Lambda greater than 1. A grows these vectors. Right? Lambda greater than 1 it grows these vectors. Lambda 0 smaller than lambda smaller than 1. A shrinks them. Can you read this? I can't read this. Shrinks them. Lambda equals 1. A preserves them. Lambda imaginary, bizarrely enough, is rotation. And lambda equals 0. A crushes these ones. Crushes them. And then lambda smaller than 0, you get the same things. Lambda smaller than 0, we have flipping involved. Right, so if you have an eigenvalue minus 1, then that A times that vector will flip the other way, and then flip the other way, and then flip the other way, right? And then it might be growing or shrinking and so on. Okay, good. All right, so, but all along there's been this problem that this is going to be a hard thing to figure out, right? This is a bit nasty. We know how to do rate reduction, that's totally good, but this is going to be hard to figure out. Yes? Yes. These words here? Yeah. Okay. So generally a bit of a fail here. So rotation can't preserve any direction because it's rotating. It's not keeping anything, it's turning everything. So it seems to be against our whole eigenvector idea. But yeah, and then this is because math. And then this is lambda 1. This thing? This one? Yeah, so this was just a way of writing a. It wants to rotate vectors this way. Yeah. Minus 1 plus 1 will be that one. So, no, it's good. So in general, theta is, what is it, cos theta, gosh, minus sine theta. Did I get that right? Yeah, sine theta, cos theta. I getting that right? Okay, all right. We good? Okay, we're going to go into this other place. Let's do it. Let's do it. That's good. That's done. Done. Oh, yeah. One super bonus. For some reason, I have it in very small letters here. Types of eigenvalues. Amazing things that will happen. So these are spoilers, because you should do that in science. It's OK. And if A is symmetric, then, and we've had sort of a sample of it here, then A's E vectors are orthogonal. So that's kind of great, because we like orthogonal bases, right? We made I, J, and K. We just really like orthogonal bases. It makes a lot of sense for us to use them. And if we have a symmetric matrix, then that's always the case for them. That, and, it's going to be tilted in some way, but if they have orthogonal matrices. And then even more, I suppose, is that in the right basis, or if you view it in the right basis, A is a diagonal matrix. A is simply a diagonal matrix. Sorry. A diagonal matrix. That's crazy. So you've got this matrix full of numbers. It's symmetric. But if we move away from I, J, K, whatever the basis we have, this big, standard Rn basis, we get the right basis. It turns out that matrix is really diagonal. And we're going to call that thing capital lambda. Lambdas. That is delicious. Okay, so I did that. Okay. All right. Good. Okay, so our problem is, so here's the problem. But we have a big problem. Big problem. Row reduction of A minus lambda I, this thing with zeros here, the zero vector, is horrible. Does not scale, right? We're going to have lambdas on the bottom and also just a total mess. So we want a better way to do this. So we need a better way. We need a better approach to finding when, this is because this is the same thing, a to the minus lambda I does not exist. This is another way to think about what we're trying to say. We want to have the case, we want to find those lambdas, and the example we just had, there are only two. Out of all the possible lambdas here, there are only two, for which a to the minus, this inverse does not exist. Which is to say that, right, again, this fundamental equation we have equals 0 has non-zero solutions. All right, so anything that helps us do this, we'll do it. All right. And in general, I haven't said much about this. There's a lot of numerical work that goes with matrices, right? And that's another course you can take after this. But calculating inverses is hard. It's a nasty thing to tell your computer to do. If you don't like your computer, you can do that, but it's a nasty thing to do. So we try to avoid it. That's why we did LU decomposition, apart from the fact that it's just sitting there. But it's much better to do that than inverses. All right, so determinants. We're just going to do it. Okay, craziness. Okay. There is a better way. So the better way determinants, as usual, we have a very boring, ridiculous name. Okay, but that's what it is. You want to speak in the parlance of linear algebra. bore your friends to death, then you will have to say the word determinants. Okay, so let's do this. This is fun. This is fun. Okay. So let's imagine we're going to take a simple matrix. This is a completely different game now, right? So have this little example. We're going to work through some aspects of it. And I'm going to say, which one? Yeah, 2, 3, and 1, 4. 2, 3, and 1, 4. So 2, 3, 1, 4. It's a nice little matrix, okay? If we could find out that this has an inverse, all right, we could do that. But we want to sort of, and the way we would do that is our row reduction method from the start. We went through and found inverses. Okay. So recall finding inverses by this. We put A, right? And we do row reduction. And then we'd end up with an identity on this side and a to the minus 1 on this side. Right? We did this. Yeah? When does this not work? When can we not get the identity on this side? Say it again? Ah, yeah. When it's the identity matrix, it's still there, actually, because you've got identity, 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 identity. The inverse of the identity is the identity. Okay, so we're going to have n by n's. Oh, yeah, okay, you said the right thing. Yes, of course. And yes, right. What was when we were doing this, how did that manifest? So you're not allowed to know about rank. Pretend you know about rank. We were doing this, right? We do row reduction, row reduction, row reduction. We put all these zeros here and all these zeros here. What stopped us from doing that? Right, great, okay. So this is way back in the, I know, so you've learned too much. Okay. So this failed if one or more pivots equaled 0. So, again, it's going to be kind of that idea, but we have a lambda inside of our matrix. So we could just find the pivots, but right. All right, we're going to learn all about determinants. That's what we're doing. Okay, so let's say we have this thing. Yeah. Right. Right. So we could do this. So if we did this, we'd find a to the minus 1, in this case, is 1/5. And then it's 2, 4, minus 3, minus 1. Yeah, and actually it's a minus 5 there, right? Look at that, right? What am I doing? What's wrong? What have I done wrong? Yeah. No, that's 4 minus 9, so it has to be, yeah, it's over that. Yep. Minus 1. Yep. What am I supposed to be doing? You're right. Sorry. These ones? Yeah. Thank you. Right. Yeah? 3, 1? What am I doing wrong? The 4 and the 2, right? And then these are negatives. Okay. All right. So we good? Okay. All right, so if we did this, we'd find this. We're going to, and we did figure out a formula for it. So you could use that. All right. This number is going to be the important number. Right. This is A's determinant. Now, we could have any factor out here, it's true, but it will turn out that this is a determinant. And we could set, if the determinant is 0, then this thing explodes into flames, right? There's no inverse. So that's the idea. Okay. All right, so let's draw, I want to draw a picture. I want to get this right. Wow. All right, people, good, good. So we've got this one, straight lines, okay. Okay, so I'm going to do this. So I'm going to take the rows of this matrix, two, 3, and 1, 4. So let's plot those. I'm going to end up with a 7. Okay, 7, 4, 3, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5. Okay. All right, so let's plot these vectors. So this is 2, 3. So 2 and 3. Let me get this right. Apparently this is hard for me to get right. So 2, 3. So we take, so here's a weird thing, weird observation. Make a parallelogram. We'll make parallelepipeds because that's funny. Make a parallelogram out of the row vectors, out of A's row vectors. Okay? So this one is 2, 3, 2, 3, and the other one is 1, 4. 1, and then up to here. Draw this well. Okay, and what I mean by this is, so here's, let me write it like this. This is 2, 3. This is 1, 4. So this is row 2. And this is row 1. And then let's stack them together and add them again. We're going to make a parallelogram. So this is 3 more of this way and 2 this way. So I want to be at about here. Right. And the box is going to be like this. What is this madness, you ask? Okay. I have to add a webisode today, I think, because I'm not going to get through it all. Okay, so what's the area of this parallelogram? Seems like a ridiculous thing to ask. Okay. What's the area here? All right, so it's going to be, this is a 4, this is 7, this is a 3. All right, and then we've got these little boxes here, so that is useful to do. All right, so let me fill those in. Okay, so this is, these two triangles match up with each other, so we could combine them. These two rectangles, they're sitting there, they're good, and we have these two rectangles, triangles as well. So it's going to be the overall area, so it's 7 times 3. 7 times 3, so this is the overall thing. And then we're going to subtract off these pieces. So there's a 3 by 1 here. So let me write as a 3 by 1, 3 by 1. This is a half 2 by 3, a half times 2 by 3, and this is a half 2 by 3. And then I think we're there, and there's this one, 4, this is a half 4 by 1, a half 4 by 1, a half 4 by 1. So it's 7 times 3 is the whole thing, then we have 3 by 1, I'll just write them out properly, minus 3 by 1, and then we can add those two triangles together, minus 4 by 1, minus 2 by 3. See if we get this right, which might be amazing at this point. So it's 21, minus 6, minus 4, minus 6, so minus 16 equals 5. So that's sneaky and strange. This is what we'll begin to call the determinant of A. It is how much area for a 2 by 2 in a parallelogram. In a 3 by 3, we're going to make parallelepipeds. 4 by 4, we're not even going to try. And we're going to think about, as we mess around with this matrix, how this area changes. Okay, interesting. Good. Good. Okay. Maybe that's where we get to today. All right. Okay, let's go. Now, if you want, you could draw the same parallelogram for 2, 1, and 3, 4. Right? We could take the columns. And you'll find you'll get the same area 5. Strange. Okay. All right, so, in general, for 2 by 2, let's say we have A, B, C, D. Right, so we're going to have these 2 rows. Let me put a note here. So a note, no, I'm not going to do it. I'm not going to do it. All right. Okay, so A, B. So let's say we have this. So here's our parallelogram. And this is going to be A. This is B. This is, well, let me make this one. No, this way. A is here, B is here, so it actually matters. B is here. This will be C and D. And then when we add them together, we get B plus D here and A plus C here. Good. Good. So this, right, so the area of this thing equals the area of the whole thing, B plus D, times A plus C. And then we're going to have to subtract off these pieces. So let's figure out what they are. There are these 2 triangles. We can join those up. Let me maybe hash them in the same way. There is these 2 triangles here. We can join those up. And then these guys are the same as well, here. Right. Good. So it's the whole area minus, what do we have here? This is up to DC, right? So minus DC, because we're putting those 2 together. This is a height of B and C, so this is a height of B and width C. So we get 2 of those, minus 2BC. Right, that connects to here. This connects to here. No, connects to here. And this one is A times B. So we have minus A times B. That triangle and that triangle. All right, so let's multiply it out. We have AB plus DA. We're just going to do it. Plus BC plus DC minus DC minus AB minus 2BC. Let's see what happens. These cancel. These cancel. This one cancels with one of these. So we get a general formula, AD minus BC, which you will know if you've done, people have taught you about determinants in different ways. That's the formula for a determinant for a 2 by 2. Okay, so that's going to work for our little equation, or for our little, so example was 2, 3, 1, 4. Let's get it. So this, we'll call it the determinant of A equals, and here's a notation thing. This is very important. We're just going to put, and this is, it's not very obvious at all, but we'll just put lines. Right, so straight lines indicate determinant. So using our formula, it's AD minus BC. So AD minus BC, it's 2 times 4 minus 1 times 3. So it's 8 minus 3 equals 5, as before, right? So here's a bit of a weird thing. So what if we swap the rows? Swap A's rows. What happens then? Determinant of, right, to make B. Let's say we'll call it B. Determinant of B in this case now is 1, 4, 2, 3. So it's 1 times 3 minus 2 times 4. 3 minus 8 is, so that's a weird thing. There's a minus sign. We're talking about areas of parallelograms, and you can think of it like this. So the ordering of the vectors mattered. This was our first row, here's our second row. We ended up with a plus 5. If this is our first row, and that's our second row, we get a minus 5. So there is a rotation handedness built into these things. So the order of rows can introduce a negative sign. Negative sign. But it's still 5, right? We're still going to have 5, still the same area, still the same parallelogram. We just built it differently. We said, here's the first part, and here's the second part. Okay. So that's an observation. Right. Wow. Maybe I talk slowly. That's an observation. And so we're going to make this kind of grand statement about these things in a second. Let's just observe a couple of things. So the simplest, so some observations to finish this off. The simplest 2 by 2 is the identity matrix. And what's its parallelogram? Very simple, right? It's just the square, the unit square. This is 1, 0, 1, 0, and this is 0, 1. Area equals 1. Right? The determinant of the identity is 1. We're going to use that little formula we just made. And we can write it like this. The determinant of the identity is equal to 1. So this is 1, 2. Determinants add in a very special way. Right, I'm going to finish this. It'll take me 4 or 5 minutes. Okay. Yeah. So here's the example. Again, we've got our 2, 3, 1, 4. 2, 3, 1, 4. This is, again, determinant. Right? It's not the matrix. Determinant equals, this is an observation, equals, I'm going to break this matrix down into 2, 0, 1, 4 plus 0, 3, 1, 4. So top rows add to form this row to 2, 3, to this vector. These are the same rows. These are not adding. Right, so if we were adding 2 matrices together, we'd end up with 2, 0, we'd end up with 2, 3, and we'd end up with 2, 8 on the bottom. We'd just add everything together. But for determinants, it's if you have to add things row by row. So let's look at this picture. We have our parallelogram for this one, this area. This was 5. What's the area of this one? So now it's a 2, 0. Yeah, 2, 0 is our first vector. So it's a simpler one. That's what's happening. This is, say, 2, 0. And this is 1, 4. So it's a simple looking thing. That's 1, 4. And the area of this one is 8. There's an 8 in here. If you compute it, various ways we've done it, 2 times 4 minus 0. And then we have this one. What's its shape? So this is our first vector here, second vector. Here was our first vector, here was our second vector. In this one, we've got 0, 3 actually. 0, 3 here. This, and 1, 4. So it's skinny actually. 1, 4. 1, 4. So it looks like this. It's sheared in that direction. And the area of this, it's 0, 4 minus 3. It's actually minus 3. Because negatives can sometimes happen. So 5 equals 8 minus 3. And what we're trying to do with this madness here is these shapes are simpler. Simpler shapes. So if we can take this more complicated parallelogram and we can do it in large dimensions and we start to break it into simpler and simpler shapes, things are going to be better. So let's see, we can also do, this one, 2014 equals 2004 plus 2100. Just 1 second. Yep. So we're breaking down the bottom part. These guys add. They stay the same. And what do these pictures look like? So this is this one. Right, it's our thing like this. We've got an 8. This one is 2, 4. This is a very simple shape. It's 2, 4, 2, and 4. So this is very simple. Area is 8. What's the area of this last one? 2010. It's actually this vector, 2010. Zero area. And then this thing, we can simplify this even further. This is equal to 4 times 2 times the area of the unit square. All right, so let me write down the last thing. So the goal will be to express the determinant of A as some multiple of the determinant of the identity matrix, which equals 1. So that's what we're going to work on next. I'll add a few more pieces, I think, on the web, so you can do some of the questions in the assignment. And we are back on Tuesday. But determinants are strange, and it will take a while. All right.
Thank you.